In a previous video, when we were talking about how to develop the equation for a line from a scatter plot, we were just using visual inspection to decide if a line would possibly be a good fit for some data. And we said that there was a better method coming, and that better method is coming today. It's called linear regression. So linear regression is just a way to decide how good is that model, how good is a line as a model for the data. To get an idea for how it works, we're going to make use of a simulation from an organization called PhET, which stands for Physics Education Technology. This is really a fantastic organization. It comes out of the University of Colorado, and they just use lots of different simulations to help us visualize some kind of difficult concepts in science and technology and math. So we're going to visit PhET and learn about the basic idea behind linear regression, and then go into some details about how we can use it after we're done with that. So now we're in the simulation that helps us learn about least squares regression or linear regression on the PhET interactive simulations site. And we're going to grab one of their data samples, height versus shoe size, and just put that on the screen. So here we have a scatter plot. This is collected from data where the U.S. shoe size is on the horizontal axis and the height in inches of a person is on the vertical axis. And we're going to find out how good of a fit a line is, or how we can determine how good of a fit a line is. So you'll notice that there's a blue line already on this graph, and that line has its equation up in this little salmon-colored box here. Y equals mx plus b, the standard equation from math for this line, has a slope of 0 and a vertical intercept of 0, so that's why it's a horizontal line sitting way down at the bottom. What I'm going to do is I'm going to turn on something called residuals. So this is just a line that represents, the length of this line represents the difference or the error between my points and my line. All of these errors are positive. The points are bigger than the line. Watch what happens when I start to change the vertical intercept. So I start to slide this up, the error gets smaller. In other words, I'm getting a better fit for this line. Now I can change the slope as well. Again, the residuals, the error, starts to go down. If I keep tipping this up, now all my errors are negative. Well, if you took the average error, that could be a way of deciding how good of a fit your line is. But when I have a line that's a fairly good fit, some of my errors are going to be positive and some are going to be negative, and they might end up canceling each other out and telling me that I have no error. In other words, my line is a perfect fit. But that's not really true, because the positive and negative errors are just canceling each other out. So I'm going to pull that back down to 0 again, and I'm going to change the way that I measure error. Instead of the residuals, I'm going to take the residuals and square them. So now instead of lines, we just have squares that are the size of the error. Well, this makes a lot of pretty large purple squares here. Another thing that happened when I clicked on that was there's a sum line. That purple bar graph shows us the size of the sum of all these squared residuals. We will have minimal error when we can minimize that sum. So we know that we can minimize our error by increasing the vertical intercept. But that only helps so much. Now let's change the slope. You can see that all these purple squares are getting smaller and smaller, and now we actually see our sum bar graph start to get smaller. Now it starts to get bigger again, so somewhere in between there's a kind of a sweet spot. Now let's change the vertical intercept a little bit. It got bigger, now the sum got smaller, and there was a sweet spot in there. Now I'm going to adjust this a little bit, find my new sweet spot, and adjust vertical intercept, see if I can get it even lower. It looks like it's probably about as good as I can do. Well, if I look up here on the equation of the line, it says a slope for this line is 1.65 plus 51.1. So that tells us something about what would the equation be that we've chosen that we think fits the best. Now, calculus, a branch of mathematics, has a way of finding out what is the absolute best fitting line that you could possibly have. So when we click on this, they will give us that line for this example. Click on best fit line. We were not too far off. The red line represents the best possible fitting line, and the slope is a little bit steeper than our slope, and the vertical intercept is a little bit lower than ours, but we actually did a pretty decent job. There's one more thing that I want to do here before we leave this simulation, and I want to click on the correlation coefficient. We get this number called R, which is 0.85. We're going to give some meaning to R as we proceed. Now, no one's going to use PhET as a way to determine linear regression. That's probably not a very efficient tool. So we have a lot of other options available to us. One of them, which we'll explore a little bit today in this video, is called Graphical Analysis. This is a Chrome app that works on Chromebooks, and you can take data from lots of different sources and then analyze it for regression. There's a graphing calculator, Desmos. I really like Desmos. I think it's a pretty powerful tool. And what I think is really nice about it is it comes in a mobile app, and so you can use it on your Android or iOS device anytime you want, even after you're done with school and might need to do some kind of calculation. Another one is Google Sheets, or basically any software that gives you a spreadsheet will do linear regression. And another tool that many high school students have is your graphing calculator. TI-80 anything graphing calculator does a really good job of finding linear regression if you put some data in there. Let's take a look at graphical analysis and analyze some data just so you can get a feel for how a real-life tool works for finding the best fit line. When you first open up graphical analysis, this is what it gives you. It gives you the option for gathering data from sensors or sharing data, getting data from somewhere else, and also manual entry. What we're going to do is manual entry here, so I'm going to click on that. And then it brings us to a graph. So we have a graph here and then a data table over on the right-hand side. So I'm going to put some data in this data table. I'm going to click on column options, and I like to make sure that I know what I'm graphing here. So I'm going to click column options for this, and I'm going to change this from X to weight, car weight. So what we're going to do is we're going to be putting some weights of cars in our independent variable axis, and this will be in 100 pounds. That will be our unit, hundreds of pounds. There's some other stuff on here that we're not going to pay attention to right now. We're just going to give it a name and put in a unit. When I click apply, it changes the heading on that table. And then the other thing that we're going to track, this will be the dependent variable, will be, instead of Y, I'm going to change this to gas mileage. And this will be in miles per gallon, or MPG. So I click apply, and that heading changes as well. So now I have some data. Our first car weighs 2,700 pounds, and its gas mileage is 25 miles per gallon. Our next car, 35 pounds, 19 miles per gallon. 3,900 pounds, 16 miles per gallon. So at this point, this is probably pretty boring for you to watch, so I'll probably speed through the video and enter the rest of my data. It's a pretty large data list. Okay, so all my data is in place. I'm going to make a few changes here. I'm going to change my size of my graph. My left axis, I'm going to make this go down to -1, my left of my x-axis. And my y-axis, I'm also going to make it go to -1 because I want to have my two axes appear on the graph. I'm not going to put a title on here, although it would be nice to do that. Okay, so here's my scatter plot of points. Now, here's how we find the best fitting line in Vernier Graphical Analysis. Once the scatter plot's in place, we go down here and we click on this little button, and then we click Apply Curve Fit. So Apply Curve Fit, and I have a bunch of options here. There are lots of different options. We are always going to choose linear because it gives us the best results and they're the easiest to interpret. Then I click apply, and a little box pops up here, and it gives me some information. It tells me the range, which I don't really care too much about. It gives me the general equation of a line, y equals mx plus b. That's not useful information because I already know that. But now it gives me the slope. It tells me what m actually is, and it's a negative 0.994. That's the slope of this line. It's negative. I guess that makes sense because it means that the heavier the car is, the lower the gas mileage is. And the vertical intercept is 53.01. So that means it's kind of a nonsense number, actually. That means if the car weighed 0, its mileage would be 53.01, but I don't think that's really useful information. But it is part of the equation of our line. Now below that is an R number. Now R is a measure of how well the line fits. And it's negative 0.9165, which means this is probably a pretty decent fit for this kind of data. We'll talk a little bit more later about what R really means and when R is a good value and when R is not good enough of a value to use a line as a model. So now let's talk about R. The name for R is called the correlation coefficient. When R is positive, it's greater than 0, that means it's a positive slope. And when R is negative, that means that there's a negative slope. R ranges from -1 to +1. It's never outside that range. When R is 0, that means there's no fit between the line and the points. A line would be a terrible model. When R gets to the extremes, closer to -1 or closer to +1, that means you have a good fit. There's another number that some regression analysis tools give us, and that's called R squared. It's the coefficient of determination is the name for this, and because it's squared, there are no negative numbers. So this range is just from 0 up to 1, and this has a little bit easier to understand meaning. If R squared is 0, that means there is 0% chance that your line will predict a correct value of the dependent variable based on the independent variable. If it's a 1, then that means your line is 100% predictive. In other words, you put in any value of the independent variable and it will predict 100% correctly what is the dependent variable value. So you want R's that are close to 1 or R squareds that are close to 1. So how good is good enough? It turns out that it depends a lot on how much control you have over your experiments. If you're working in something like biology or economics or social sciences like psychology, there's a lot of things that you just cannot control. And so you're lucky to get a R squared value or an R value that's in the 0.4 range. And that means you just don't have really good predictability, but sometimes it's the best you can do. In physics, we often have very, very good control over our experiments, and in chemistry as well. And so lots of times we're shooting for an R value or an R squared value that's bigger than 0.99 or closer to -1 or +1 than -0.99 or +0.99. And so because we have tight control, we can be really picky about our R values. So the purpose of this was just to give you an idea of how we can use a tool called regression analysis to make a better decision about if a line would be a good choice as a model for some experimental data or if we should look for something else. So in future videos, we're going to have to take a look at what do we do when the regression analysis tells us probably we shouldn't use a line.